As usual, the marginal cases always cause us a little bit of headache. And so you may be wondering, what happens if we know that our contour is on the right half plane, but part of that contour extends along the imaginary axis. And so you may be wondering, what happens if any of our poles or zeros are actually on the imaginary axis? So what if they're on this boundary of this contour that we're talking about? So from a technical point of view, for the proof, essentially what we do is we make infinitely small detours around these poles. So if we have poles here on the imaginary axis, then we make these little detours around them in order to make sure that our poles, those poles are not the ones that we count for being inside the contour. So now it's also interesting to observe what the effect is of having these poles on the imaginary axis. And so what ends up happening, remember, this radius is kind of infinitely small. And so we said that the angle alpha, which is what is being plotted out for the Nyquist plot, what ends up happening there is that so this is equal to essentially the sum of all the zero angles, and then minus the sum of all the pole angles. And so what ends up happening is if any of these angles experience a very sharp change in their value, then that's going to appear in alpha. And so if we look very closely around one of these little detours, this means that initially a test point might be here, at which point the angle that this pole needs to look at that test point, S0, is minus 90. And that's true again here. And then because this arc is infinitely small, because the radius is infinitely small, the next test point is going to be right here. And that is going to have an angle of plus 90. And so that means that this phi angle has immediately jumped from minus 90 up to plus 90. And so that is demonstrated by a change in alpha of 180 degrees. So it causes this instant jump in phase. And so for every pole or zero that we have in along the real axis, or sorry, the imaginary axis, that's going to cause a 180 degree jump at that particular frequency. So if this frequency was, say, minus 5i, then at 5, you're going to have, because this is also going to be at 5i, at 5, you're going to have this jump in phase. And so that's something that we're going to be able to observe on the Bode plot. You'll see an instantaneous jump in the phase. Or on our Nyquist plots, what's going to happen is that we're going to get these arcs at infinity. And so this means that all of a sudden, the Nyquist plot is going to go 180 degrees and then pick up where it left off. So it may have emerged out of 0, gone to some value, and then once it hit that frequency, it would go 180 degrees and then pick up where it left off. And so similarly, if you had a double root, a double pole, for example, at 0, then that would be the same as 2 angles contributing 180, and so that would be a jump of 360. And so that would correspond to a full loop all the way around and back to where you started. And so these big loops are called these arcs at infinity. And so we'll see examples in class of when this happens.